Hi all, so welcome to another video of linear control systems. Today we are going to discuss about the problems based on Ruth Hurwitz criterion, which is used for the stability analysis of a system. So the first problem is construct the Ruth array and determine the stability of the system represented by the characteristic equation s raised to 5 plus s raised to 4 plus 2s cube plus 2s square plus 3s plus 5 is equal to 0. Comment on the location of the roots of characteristic equation. Okay, so here in the question the characteristic equation is given. Okay, so the given characteristic polynomial is fifth order because the highest power of s is 5 here, so it is a fifth order equation, and so it has 5 roots. So since the highest power of s is odd here, form the first row of Ruth array using the coefficient of odd powers of s, that is s raised to 5, s raised to 3, s raised to 1, like that. And the next row, okay, the second row using the coefficient of even powers of s, that is s raised to 4, s raised to 2, like that. Okay, so we are going to construct the Ruth array. Here the first row is s raised to 5. So here we are writing the coefficient of alternate powers of s, that is the odd powers of s. So here the coefficient of s raised to 5 is 1, and the coefficient of s cube is 2, and the coefficient of s is 3. So 1, 2, 3 will be the first row. Okay, and the second one s raised to 4. S raised to 4, here the coefficient of s raised to 4 is 1, and s square is 2. So it is, and again there is a constant 5 here. Okay, alternate coefficient we have to take. So s raised to 4, s raised to 2, and 5. Okay, so 1, 2, 5. And in the left side we can keep the correct Ruth array. In the right side we can do the calculations. So the next we have to find the s raised to 3 row. Okay, s cube. So it can be found using the equation, that is 1 into 2 minus 1 into 2 divided by 1. Okay, and again the second element is 1 into 3 minus 1 into 5 divided by 1. Okay, so the first element becomes 0 here, and the second element becomes minus 2 by calculating the values. And here the first element becomes 0. Okay, so we can't proceed further for determining the s2 and s raised to 1, s raised to 0, because the first element here is 0. Okay, then all the other values will become infinity here. So here we are going to replace this 0 with any arbitrary constant. Suppose here we are taking it as e. Okay, this is the constant e we are taking. So replace that 0 with e. Okay, and write in the real array, that is s3, it is e minus 2. Okay, instead of 0 minus 2 we have to write e minus 2. Then in the next row s square. So after replacing the value of e here, we can proceed further, that is we can find s raised to 2 using this e. Okay, so the value will be s raised to 2 will be e into 2, e into 2 minus 2 into 1 divided by e here, divided by e. Okay, and the second element will be e into 5. Okay, e into 5 minus 1 into 0, here it is 0. Okay, divided by e into 5 minus 0 into 1 by e. Okay, and by calculating we will get it as, okay, 2e plus 2 by e, and here it is 5. Okay, so we are just writing that values here, 2e plus 2 by e and 5, and s raised to 1 can be calculated as 2e plus 2 by e into minus 2 minus 5e divided by 2e plus 2 by e. Okay, so here we can see the calculation, 2e plus 2 by e into minus 2 minus 5 into e by 2e plus 2 by e. So by solving we will get as s raised to 1 as minus of 5e square plus 4e plus 4 divided by 2e plus 2. So here we are writing it. Okay, and s raised to 0, this term into 5 minus 2e plus 2 by e into 0, here it is 0 divided by this term. Okay, you can see the calculation here, and this entire term will become 0, and here we can cancel this large term, and we will get s raised to 0 as 5. Okay, and after obtaining the Ruth array, we have to substitute. Okay, at last we have to substitute that e as 0. Okay, and the correct Ruth array becomes 1 2 3, then 1 2 5. Instead of e, just substitute 0, and the s raised to 2, the first element in the s raised to 2 row will become infinity, because the e here it is in denominator side, so it becomes infinity 5. Then the s raised to first element in the s raised to 1 becomes minus 2. Okay, by putting e as 0, we will get as minus 4 by 2, so because that is minus 2, and s raised to 0 is 5. Okay, so by substituting the value of e as 0, we are obtaining the first column of our Ruth array like this. So by observing the first column of the Ruth array, we can see two sign changes there, that is infinity to minus 2, the first sign change, and minus 2 to 5, that is the second sign change. So which means two roots are lying on the right half of S plane, and the remaining three roots are lying on the left half of S plane. Okay, so here the system is unstable because two roots are lying on the right half of S plane, so the system is unstable. Okay, we know that for a system to be stable, all the roots must be lying on the left half of S plane. Okay, so here two roots are lying on the right half of S plane, hence our system is unstable. Okay, so that's about the problem. I hope it's clear, and we are moving to the next type of problem. So here we have to determine the range of k, the unknown value of k, for stability of unity feedback system whose open loop transfer function is g of s is equal to k by s into s plus 1 into s plus 2. So here normally in the questions we will be giving the characteristic equation. Characteristic polynomial will be given, but here the open loop transfer function g of s is given. Okay, so we know that the characteristic polynomial will be the characteristic equation will be the denominator polynomial of our transfer function c of s by r of s, c of s by r of s. Okay, so if you are finding this c of s by r of s, the denominator polynomial when equating to 0, it becomes the characteristic equation. So for finding c of s by r of s, we know that the equation is g of s by 1 plus g of s into h of s. Okay, 1 g of s by 1 plus g of s into h of s. So here the g of s, the value of g of s, that is open loop transfer function, is given, and we know that it is a unity feedback system, so the value of h of s will be equal to 1. Okay, so initially we have to find the characteristic equation, and here the closed loop transfer function, okay, c of s by r of s is can be find using the equation g of s by 1 plus g of s, and substitute the value of g of s here, and we will get the c of s by r of s as k by s into s plus 1 into s plus 2 plus k. Okay, and the characteristic equation is the denominator polynomial when equating to 0, it becomes the characteristic equation. Okay, and by opening the bracket we will get it as s cube plus 3s square plus 2s plus k is equal to 0. Okay, and we have to construct the Ruth array for this characteristic equation. So by constructing the Ruth array, the first that is the highest power here is s3. Okay, so we have to first write the coefficient of s3 s raised to 1 like that. So s3 row is, the coefficient of s3 is 1 here, and the coefficient of s is 2, so 1 2, and then the next row s raised to 2 row. Okay, here the coefficient of s square is 3, and the constant here is k. Okay, so 3k, and for finding s raised to 1, we know that 3 into 2 minus 1 into k divided by 3, so it becomes 6 minus k by 3. So just write the 6 minus k by 3 here, and s raised to 0 can be found using 6 minus k by 3 into k minus 3 into 0 divided by 6 minus k by 3. Okay, so it's 6 minus k by 3 into k minus 0 into 3 by 6 minus k by 3. So 6 minus k by 3 is cancelled here, and you will get s raised to 0 as k. Okay, k. And for the system to be stable, we know that there should not be any sign change in the first column. Okay, so hence choose the value of k. Okay, we can choose the value of k so that the first column elements are positive. Okay, positive. So from the s raised to 0 row, for a system to be stable, the value of k should be greater than 0. Okay, so here only the value of k is there. So for a system to be stable, the value of k should be greater than 0. And for s raised to 1 row, okay, s raised to 1 row, for a system to be stable, the 6 minus k by 3 value should be greater than 0. Okay, which means we know that 6 minus k should be greater than 0, and in fact we will get it as the value of, that is 6 minus k should be greater than 0, which means the value of k should be less than 6. Okay, so from the s raised to 0 row, the value of k should be greater than 0, and s raised to 1 row, the value of k should be less than 6. So we will get in a conclusion that the value of k should be in between this 0 and 6, that is 0 less than k less than 6, that you can see here. On the s raised to 0 row, the value of k should be greater than 0, and for s raised to 1 row, the value of k is like that. Okay, 6 minus k by 3 should be greater than 0, and which means k should be less than 6. Okay, and in fact the range of k for the system to be stable is 0 less than k less than 6. So that's our solution for the system given. Okay, I hope the question is also clear. So thank you.